diastereomers. So enantiomers have mirror image structures, whereas diastereomers are not. And anything that is not mirror image structure, that would be diastereomer, even though they are essentially isomers in space. So enantiomers, typically we can say that they have a plus and minus. Now these are called the rotation, that is the difference in properties. Enantiomers have almost identical properties. Their chemical properties are very similar or almost nearly identical. The only thing that differs in them is their enzymatic property. They deal differently with enzymes, but they are essentially have a rotation. So place polarized light can be rotated differently through the enantiomers, and we call one of them dextrorotatory. The other one is levorotatory. And again, do not mix up the dextrorotatory, levorotatory with D and L, which we often use for the Fischer projection. They are completely different concepts. They have nothing to do with the rotations. So enantiomers, therefore, can be, these are properties that are experimentally verified. We cannot always predict what the property would be of this rotation, but often we would link them with an absolute configuration of the molecule. And the absolute configuration tells us, we determine the absolute configuration typically by the Kahn-Ingold redox system, so R or S, or by the Fischer projection, we can say D and L. The D and L is an imperfect system. That was the first one introduced by Emil Fischer, but the reason it's imperfect is that if you have multiple chiral centers, it doesn't give you information about many of them. It only gives you for one. And so the diastereomers could be any structure that are not mirror image. So cis and trans are diastereomers. E and Z are diastereomers. And if you have multiple centers, if you change one or leave the one intact, then they will be diastereomers. And these two terms also gives us another issue, enantiotopic and diastereotopic. Now, enantiotopic and diastereotopic relates to the phase where, because you can start with something that is achiral, but they can be added. A reagent can add either a hydrogen or some other molecule to that, as we have seen in case of double bonds, from two different sides. And that will give you two enantiomers or two diastereomers, depending on the type of molecule you are dealing with. And enantiotopic compounds are more common than diastereotopic compounds. Nevertheless, by doing that, we get a mixture. We get a racemic mixture, and that is also related to chirality in the sense that if you have equal amount of the dextrorotatory and levorotatory compound, the same compound in two different stereoisomers, that will give you a zero net rotation. So if you have equal amount of plus and the minus enantiomers, that gives you optical rotation is 0. So this is therefore, even though they are individually chiral compound, that are called racemic mixture. So both achiral compound and racemic mixture have are the anisotropic and diastereotopic brings into another new information, that something that we did not talk about before. And let me give you an example of that. This is all of these you need, right? Just wanted to go over that very quickly. Let's assume ethanol. So ethanol, of course, has no kind of thing. This is an ethyl compound, regardless of which carbon you look at. There are multiple hydrogens attached to each one. So they are ethyl. However, the position of these two hydrogens are actually different. And we define them as pro-R and pro-S. Okay, so this prochiral relationship. Why is that important? Because the reason we know that is important is that you can do an experiment in which you replace a hydrogen with a deuterium. So let's do that and look at this one. And let's take this one. And then treat that with alcohol dehydrogenase. The alcohol dehydrogenase is very specifically picks up in this molecule. It will pick up the deuterium, okay, and convert it to acetaldehyde. This is an achiral compound, but the important thing is that it would not pick up this hydrogen. It is specifically going to pick up this deuterium. Okay? And likewise, if you put the deuterium in the other hydrogen, the entire deuterium will remain, and the hydrogen will be picked up by this enzyme. This experiment has been done, and therefore, that's the reason we kind of have to define them. And how do we define them? When you look at this hydrogen, we give it a higher priority than the other hydrogen, right? And then figure out their rotation. So if this is the lowest priority, then we have 1 to 2 to 3. This is actually what we call a pro-R hydrogen. So it's HR. And the other one is pro-S, obviously. And alcohol dehydrogenase specifically picks up pro-R hydrogen. And giving you acetaldehyde. Likewise, the reverse reaction also can happen. Alcohol dehydrogenase can also catalyze that reaction, which goes in the other direction, starting from acetaldehyde. That can be converted back to ethanol. And during that time, now we can actually look at the different phases of the molecule. And the phases, depending on which side, is it coming from the top or from the bottom? So from the top, the hydrogen can be added like that. Or from the bottom, which is from the other side, essentially, the hydrogen can also be added. The top phase is called the D phase, and the other side of the phase is called the C phase. And depending on how they add, it will also generate the alcohol accordingly. And so this hydrogen, of course, will be retained, but the new hydrogen would come from the top, and essentially, again, if you add deuterium in this case, that is going to add deuterium back to the same position. So this reaction is very stereospecific enzymatically done. Okay. So that is the reason we need to learn this relationship between them. I'm not going to go too much over that, but that is important for enzymatic reaction. And they become very, very specific types of molecules and particular orientation. Now, let's move on to another topic, which is called resolution of enantiomers. Now, resolution of enantiomers is an important topic mainly because enantiomers are extremely difficult to purify. Why? Because their properties are the same. Most of the time, we purify compounds which have very, very different properties. So it can be used for extraction, chromatography, and various other methods can be used to separate compounds. However, if the properties are identical, then how do you purify them? That becomes a big challenge, because the only thing that is different between the two enantiomers is their optical properties. One rotates the light towards the right, the other rotates towards the left. Otherwise, their melting point, boiling point, solubility, they're all pretty much identical. So that's why it becomes a challenge to separate enantiomers. And the general strategy that is being used is actually started from, actually let me go through a little bit of the history, because the resolution, the first resolution was done by Lou Dastur. One of the compound that he worked with was tartaric acid. And tartaric acid has this formula, COOH. Tartaric acid actually is a side product during wine making. This is formed, and what Dastur did is to look at it very critically, and he crystallized. It crystallizing makes nice crystals. And he found that there are actually two different types of crystals. They crystallize differently. And he used a magnifying glass and a pair of tweezers and picked out each separate types into two different containers. When he found that one that gave, like this is the one which is 2R3R, gives you a rotation of plus 12 degrees. So this is an extra rotatory isomer. And of course the mirror image, something that he didn't know at the time, was the other isomer, which would be S3S, tartaric acid. That gives you a minus 12 degree rotation. And also he found some of them that kind of mix together, but there is no net rotation. And he correctly figured that they are actually mixtures of the plus and the minus tartaric acid. And that's why they are essentially, they give you a racemic mixture also. And of course, it also has a mesoisomer, the one that has no optical activity. And this is actually a rare case because in most of the time, we won't get crystals that are very, very distinct from one another. Okay. They almost look alike in many other compounds. This is one of the rare cases, and he was able to do that with a tweezer and magnifying glass, something that normally you cannot do. Yes?
Does this have to do something with purifying crystals to make diamonds? Does this have to do something with making diamonds?
Yes, they actually make salt, not directly from. What I meant is like, I was simplifying the actual thing. What he did is make a salt of this, and that salt essentially crystallized very nicely. Okay. And that's what we separated. I was just simplifying the story, not going through all the details of what we had started. But the important thing is that they actually form different compounds, something that normally you cannot do. And therefore, how do you separate the enantiomers, which are mirror image structures and have identical property? So one of the ways that was approached is that if you change an enantiomer to a diastereomer, then they have very different properties. It makes it easier to separate them. So you can start with, let's say, a C plus and C minus. Let's assume that these are the two enantiomers. Then you treat it with an agent which is going to react and form a complex, but that complex will be reversible. In other words, you can reverse the reaction under certain conditions. So you use another one, which is also chiral. And that chiral compound reacts with both of them, forming C plus, B plus, and C minus, B plus. So you form now from enantiomers to diastereomers. And now the separation becomes easier because they have completely different properties. And now you can use either chromatographic methods or other methods to separate them. Once you separate them, you needed to reverse the reaction. You reverse the reaction and essentially regenerate C plus the dissolving agent and C minus plus the resolving agent. And the resolving agent can be reused. Okay? So that's the strategy, and I'm not going to give you examples. There are some examples in the text. Let's just quickly go through that. I want you to essentially understand the basic process of resolution of enantiomer. A second method is using enzymes that will react only with one enantiomer. So you can, again, that is called kinetic resolution. In kinetic resolution, you get a C plus and a C minus compound treated with that appropriate enzyme that reacts only with one. So now, let's say it reacts only with C plus, so it would essentially convert the C plus to, let's say, something X enzyme plus C minus. So C minus would be left intact, and that can be isolated. But those are, again, very specific for the enzyme. Those enzymes need to be actually identified first in order for you to carry out this type of kinetic resolution. But both of these methods have been extensively used for resolution of enantiomers. And finally, there is also chiral columns where the same strategy that we mentioned here, that can be used as a column. In which one of them will be bind to the specific column, the other one will pass through. So these are some general methods of resolution of energy domain. And I just wanted to give you the basic concept, not going through many examples of these. The final part of your section, again, I'll go very briefly over that, is that the chiral compounds can be also molecules that are not only carbon compounds. Most commonly we see chiral compounds with silicon, phosphorus, and sulfur. Okay. And there are many, many examples of that, in which case, again, we use the same principle that they are linked to different groups or atoms, and we follow the same procedure as Canning-Lord-Brillag system to figure out their RS or what the nomenclature is. But I'm not going to go through that. Nitrogen-containing compounds can also be chiral, but they are more difficult to separate, particularly the enantiomers, because they interconvert very rapidly. So if you have three different groups, they technically are chiral. That would be chiral compound. But the separation is very, very difficult because they interconvert. And again, this is the very last section of your chapter, and I'm not going to hold you responsible for any of these concepts. I just wanted you to learn the very basics of this concept, all right? And the reason I don't want to go too much over that is because of the exam. So, the exam was very, very disappointing.
That makes me feel bad.
About 55% people did reasonably well. But 55% people got greater than 80. There are 4 people who got 103.
Kidding.
What is the good news?
Good news.
Now, the problem part is that about 25% people fail, which is below 50%.